When you think of industrial disasters, you usually think of explosions, fire, or radiation. You don't typically think of pancake syrup. But in January 1919, a wave of molasses, 2.3 million gallons of it, tore through Boston at 35 miles per hour. It flattened buildings and killed 21 people. It sounds like an urban legend, but the physics are terrifyingly real. Why did a static tank suddenly decide to become a tsunami? It wasn't an accident. It was bad engineering. Today, we're going to unpack the Great Molasses Flood and use finite element analysis to show exactly how it happened. First, let's look at the patient. The Purity distilling tank was massive, 50 feet tall, 90 feet in diameter. To give you a sense of scale, that's a volume of 2.3 million gallons. Molasses is 40% heavier than water. This wasn't just a bucket, it was a gravity bomb waiting to go off. Based on the Colby report from the original lawsuit and modern analysis by Ronald Mayfield, we know there wasn't one single smoking gun. It was a perfect storm of four things: bad geometry, bad metal, bad weather, and bad management. Let's start with the geometry. The tank was doomed on the drawing board. The steel walls were significantly under-designed. The bottom ring was only 0.67 inches thick. Based on steel quality at the time, standard engineering practice dictated that wall should have been roughly 1.1 inches. That means they were operating with a safety factor against yield of only about 1.25. For context, structural codes usually demand a safety factor of 2 or higher. At 1.25, that's not a safety factor, that's a rounding error. Then there was the trigger, a 20-inch manhole cut right in the bottom ring. As you'll see in our simulation, this cutout was effectively unreinforced. It created a stress concentration factor of about 3. It took the stress that was already high and multiplied it, pushing the local steel well past its ultimate tensile strength. And to make matters worse, they used lap joints for the vertical seams. Because lap joints overlap, the plates aren't aligned, they're offset. When you pull on them, the joint twists to try and align itself. That creates a secondary bending moment that the original designers completely ignored. Factor number 2, the metallurgy. The steel they used had a very low manganese to carbon ratio. Manganese is what makes steel tough. Without enough of it, the metal is prone to brittleness. This brings us to the ductile to brittle transition temperature. For this specific steel, that transition point was 59 degrees Fahrenheit. On the day of the disaster, the air temperature in Boston was 40 F. The tank was operating below its transition temperature. So instead of stretching or yielding to relieve that stress at the manhole, the steel just snapped like glass. Factor 3, thermal shock. A fresh shipment of molasses had just been pumped in. To move molasses in January, you have to heat it, so the fluid was around 80 F. The air outside was 40 F. The warm fluid tried to expand the tank, while the cold air contracted the outer skin. This thermal battle added hoop stress exactly when the material was at its most brittle. And finally, the history. Why was it built like this? The project was overseen by Arthur Gell, a treasurer with zero technical background. No architect, structural engineer ever signed off on the plans, and it was built in a rush to beat prohibition. And here is the detail that really gets me. The tank leaked from day one. And instead of fixing the leaks, which are nature's way of saying, I'm going to fail, they painted the tank brown so nobody would notice the molasses dripping down the side. So we have thin walls, a manhole introducing stress, brittle steel, and a thermal load. But we don't have to guess how these interacted. We can build it in math. Here is our finite element analysis of the global tank. The colors represent von Mises stress. What you're seeing here is hoop stress. Imagine a belt trying to hold back a Thanksgiving dinner. The pressure at the bottom is roughly 31 psi, creating a global wall stress of about 26,000 psi. That's high, but technically it holds. Let's see what happens when we cut in the Manway. When we introduce that geometry, look at what happens to the stress distribution. Right here at the edge of the hole, the 12 o'clock and 6 o'clock positions, stress spikes. Because of the stress concentration, we aren't at 26 KSI anymore. We're pushing 75 to 80. And this is the kill shot. The ultimate tensile strength of the brittle steel was only about 60 KSI. The load exceeded the limit. The crack initiates here, propagates vertically, and the rest is history. The Great Molasses Flood wasn't a freak accident. It was the inevitable result of ignoring the physics. Codes and standards exist for a reason, because nature doesn't care about your production deadlines. I'm Clay Brittain, and this is Forensic Engineering. Hit subscribe to see how the world breaks.